Next, I'd like to state a theorem about the deformation theory of. So let's write it as theorem 5.3. The deformation theory of compact G2 manifolds. So let's take X to be a compact 7 manifold. And let's write curly M. So M is going to be the moduli space of torsion-free G2 structures on X. So let's write that as the set of torsion-free G2 structures phi comma G on X. Now, if we've got a torsion-free G2 structure phi G on X, we can move it round X just by pulling it back by a diffeomorphism of X. And there's an infinite dimensional family of diffeomorphisms, so just that set is huge, it's infinite dimensional. So if we want to get something more sensible, we want to divide out by the group of diffeomorphisms of X. Actually, it turns out it's better not to divide by the full diffeomorphism group, because that would lead to a singular moduli space, but what I call diff 0 of X, which is the group of diffeomorphisms of X which are isotopic to the identity. So basically the identity component of the group of diffeomorphisms of X. In particular, this group acts trivially upon the cohomology of X. So the cohomology classes of phi and so on still make sense here, whereas if we divided by the full diffeomorphism group, then that might act non-trivially on the homology group, and so points in M would no longer have well-defined cohomology classes of their three forms. Okay, so let's write this. Let's say let this M be the moduli space of torsion-free G2 structures modulo diffeomorphisms isotopic to the identity. So we'd like to understand what M is like broadly. So then the conclusion is that then M is a smooth manifold or you can naturally give it the structure of a smooth manifold of dimension, the third dimension, so the third Betti number B3 of X, which by Poincare duality is equal to B4 of X, because X has to be compact and oriented, and the maps from the moduli space M into the third de Rham cohomology group of X, and from M into the fourth de Rham cohomology groups of X, which take so the diffeomorphism class, let's write it in square brackets, of phi and G gets mapped to the cohomology class of phi, and again the diffeomorphism class of phi and G gets mapped to the cohomology class of star phi. So these maps are local diffeomorphisms. if you like, there's atoll maps. Local diffeomorphisms mean that for any point in here, and the small open neighbourhood of M is diffeomorphically identified with a small open neighbourhood of H3, and so on. Okay. So in the proof, you start with a single torsion-free G2 structure phi and G, then you consider small variations of that amongst torsion-free G2 structures modulo modulo diffeomorphisms close to the identity, and so you can set it up, write it as a non-linear differential equation. This is probably actually rather similar to the kinds of things Yuji has been talking about, maybe forming moduli spaces of connections satisfying curvature condition modulo gauge. So it's a similar kind of moduli problem and uses similar kind of techniques, but in this case it turns out that basically if you fix the Kerr-Moiji class of phi, or if you fix the Kerr-Moiji class of star phi, it turns out there's locally unique torsion-free G2 structure, and therefore this map from M into H3 or M into H4 are local diffeomorphisms. Okay, so the important conclusion from this is that G2 manifolds come in finite dimensional families. So this is important for constructing compact 7 manifolds with Lomé G2. Because, if your moduli space M is like this, then M might have a boundary. So it might happen. M might have a boundary of M. This is kind of rather informal, at which the kind of X phi G kind of decays, becomes singular, and breaks into simpler pieces. So X might stretch into several pieces, and then with each piece actually has Lomé contained in but not equal to G2. So you can imagine that here you might have some X, and then as you go to the boundary it might be breaking into two pieces along some kind of neck, and then each of the pieces would be simpler. So then the idea is that you construct the simpler pieces using basically Calabi-Yau geometry, and you glue together. So in order to all the constructions we know, they basically involve you kind of work out what you think is happening near some boundary point. So you kind of start at a boundary point which is not a 7-manifold Lomé G2, it's some union of singular pieces, and then you move a little way in. So you kind of deform into the moduli space, and you construct the 7 manifolds of Lomé G2 which lie at the boundary of the moduli space. And this is only possible because these things occur in positive dimensional families. Now, if G2 manifolds were kind of isolated things, if they didn't occur in positive dimensional families, then it's difficult to conceive of a way of constructing them, because how are you going to get there, really? There's no Calabi conjecture type result for 7 manifolds with volume G2. Okay, so so I'm going to tell you about the first construction, the simplest construction for 7 manifolds with volume G2, and I want to start by explaining something which has been known for a long time, which is called the Kummer construction for K3. So back in the early 90s, before I had kids and got old and got ground down by the utter pointlessness of life, I used to be kind of a bright young thing like most of you guys, and I heard about this problem of constructing compact 7 manifolds on volume G2, and I thought I'll have a go at that. And what I wanted to do is something modelled on this notion of how you construct K3 surfaces with Lonely SU2, and just kind of generalise that idea to 7 dimensions. And surprisingly, it worked. Okay, so Calabi-Yau twofolds. So compact Riemannian 4 manifolds with Lonely SU2 are all diffeomorphic to the K3 4 manifold. So most of them, so you kind of get them by the Calabi conjecture. But the Calabi conjecture is entirely non-explicit. It just tells you that some metric exists. It doesn't tell you anything about what that metric looks like. Gives you no kind of handle on it. So then the Kummer construction is an kind of approximate but explicit construction for not all but some, for some special Calabi-Yau twofold metrics. So here's the idea. So you start with a flat torus, t to the 4, with some flat metric G0. So this is just R4 with this Euclidean metric divided by, so this can be R4 G Euclidean divided by, let's say, Z4, acting by translations on here or some other lattice. And let's say sigma going from T4 into T4 act by sigma is going to take x1 up to x4, maps to minus x1 up to minus x4, where the xi can lie in R over Z. So, the fixed points, so then sigma squared is the identity. And the fixed points of sigma are 16 points. Okay, so the obvious fixed point is just the xi's are 0. But actually, if xi is a half, that's also fixed, because then a half goes to minus a half, and minus a half is equal to half modulo z. So it's xi lies in 0 or a half plus z. Okay, so there are 16 fixed points. So let's consider the quotient of T4 by this group generated by sigma. So then T4 over the group 1 sigma. This is a singular manifold of a kind known as an orbifold. And it has, with 16 singular points, which are locally modelled on R4 divided by plus or minus 1. Okay, so you can draw yourself a picture of it. I can't be bothered to draw 16 of these guys. But think about it as a kind of compact thing with 16 singular points. Each singular point is some kind of cone. Now what we want to do is to repair these singularities to make it into a non-singular compact manifold. And there's a well-known way of doing that in algebraic geometry, which is called resolution of singularities. And for this particular singularity, which in algebraic geometry it would be C2 over plus or minus 1, what you have to do is blow up the singular point. That means gluing in a CP1 at each point. And in fact, so there is an explicit and non-compact 4 manifolds let's say y comma h. So y, you can take it to be the cotangent bundle of CP1, or the tangent bundle, but cotangent bundle is nicer in some ways. And where the holonomy group of H is SU2, so it's the Clapeyron metric on there. So y is asymptotic at its non-compact end, to R4 over plus or minus 1 and the Euclidean metric on R4 over plus or minus 1. So if you want to draw a picture, think about R4 over plus minus 1 as being a kind of cone with a singular point at the vertex, which is 0. So basically singular fixed points of groups give you singular points in your quotient. So then y, it looks like the cone near infinity, and then near the singular point it changes its shape, and there's actually a CP1 sitting in here, and so in fact there's a projection map pi going from there, which is what's called resolution of singularities. Okay, so this is y and h. Now, in fact, we want to consider not just one metric on y, but a one-parameter family. So let's say G0 is our Euclidean metric here. So h is equal to G0 plus order of r to the minus 4, where r is the radius function on R4 over plus minus 1. So this means that as r gets large, this area gets small. So as you go towards infinity in the cone, h and G0 get very close. Okay. Now we can shrink h by a factor t greater than 0. Well, if we shrink distances by t, then we can consider y and t squared h. So because h is quadratic in distance, it's better to shrink it by a factor t squared. So then somehow the picture here would be this would be y and t squared h for t greater than 0 small. So if you shrink this thing down, then this bit here near the origin with the CP1 gets very small, and away from that the approximation of this with the cone gets much better. So you get that t squared h is g0 plus order of t to the fourth r to the minus fourth. So basically the r gets replaced by a t inverse of r or something like that. So in particular at radius 1, if t is small, then this is getting small. So that's a weird thing to do, perhaps. But what we do is we start with, well, our t to the 4 over 1 sigma with its metric g0. And we cut out, so radius epsilon on 2 balls about each singular point. So perhaps I'll draw a picture here. Okay, so nice big picture. Here is my t to the 4 over plus or minus 1. So I'm going to draw an annulus of radius epsilon on 2 and epsilon around each singular point. And then I'm going to erase the inner part of this. So I cut out the epsilon on 2 balls. So then near this I want to draw so here's my y and t squared h, and again I want to draw things corresponding to an epsilon on 2 and an epsilon radius here. And again I delete everything outside radius epsilon. So terrible picture. So I've got a whole bunch of copies of y and epsilon h. Y. Okay. So then I take 16 copies of y and t squared h, and I delete the region r greater than or equal to epsilon, and then I glue in the 16 annuli r lies in epsilon 2 up to epsilon. So I can identify this region with that region. So we glue this here. So I glue these regions. They're all, each of these is a copy of S3 over plus or minus 1 cross epsilon up to 2 epsilon on 2 up to epsilon. Okay, this gives a four manifold X which in fact is K3. And we can also glue the metrics so you can glue the metrics on T4 on plus or minus 1 and y and t squared h using a partition of unity. Okay, so now we have this equation t squared h is equal to g0 plus order of t to the fourth r to the minus 4, where now we're in the region r is an epsilon 2 up to epsilon for epsilon fixed. So the error, which is basically t squared h minus g0 is order of t to the 4, where t is small. So in the gluing region, the two metrics we're gluing together are quite close if t is small enough. So what we get is a family gt of metrics on x4, where gt is somehow close to holonomy SU2 for small t. To be more precise, you have an SU2 structure with torsion of size order of t to the fourth. Okay, so we have a metric which is not exactly holonomy SU2, but it's close to holonomy SU2, and we can measure the closeness to SU2, holonomy SU2 precisely. It's in some sense of size t to the 4 when measured in appropriate Banach space. So then you show okay, so with GT, where you have the SU2 structure, well, let's write it as little omega, big omega, GT or whatever, has a torsion order of t to the fourth for t small. So we have small torsion. So that's good. Okay, but there's other things which are not so bad. Not so good, which is that GT has curvature R, and if you measure the curvature of R, the curvature in the C0 norm, this is order of t to the minus 2, which is bad because when you shrunk the metric h by the factor t squared, there's some curvature living here, and as you shrink it, the curvature gets larger. So that's bad. Also, another kind of measure of how nice GT is, the injectivity radius. Delta of GT, this is a measure of the radius at which balls in your manifold look like balls in Euclidean space. This is order of t, which is small. That's again bad. Okay, so you've got some good things, some bad things, and like in any superhero movie, the good wins. Basically, if t is small, you can deform to g twiddle t, which is C0 close to GT with the holonomy group of g twiddle t is equal to SU2. Okay, so you have to do some analysis proof of that, and you're basically trying to find a small perturbation to GT which has Salonmi exactly equal to SU2, or equivalently a small perturbation of the SU2 structure which is torsion free. And then you have to work on this nearly singular manifold, and it turns out that basically this power 4 is large enough that it overcomes these powers here. Okay, so that's a kind of fairly well known kind of at least heuristic construction for Calabi-Yau two-folds, and in principle you can do the same sort of thing for Calabi-Yau manifolds in higher dimensions, but somehow nobody bothers because the Calabi conjecture is so powerful. But in the case of Salonmi G2, you haven't got a Calabi conjecture or Calabi theorem, so we use this method instead. So sorry? You join them with the partition of unity. So let's have a section 5.5 on constructing compact 7 manifolds with Salonmi G2. So if you want to know more about these, you should look in the nearly infallible books. And actually the black one has got much more details on G2 and spin 7. And that's kind of its primary focus, really. Okay, so by me in 1993 to 4, a kind of Kummer construction for compact 7 manifolds with Salonmi G2. Okay, so it's basically it's a more complicated version of the Kummer construction, and let's divide it into a number of steps. So step 1 is to start with a 7 torus, T7, with a flat G2 structure, phi 0, G0. So you just take R7 with its flat G2 structure, you divide by some lattice, sorry, that's a 7. So for example, you could just take T7 is R7 divided by Z7, and phi 0 is the usual on R7, which I wrote down before.
By flat G2 structure, do you just mean the identity sitting inside of G2?
Well, I mean the metric is flat, and that's constant. But basically, it comes from the constant, the standard G2 structure on R7 divided by some group of translations. Okay. So then, secondly, we have to choose a finite group big gamma acting on T7, preserving your G2 structure phi 0 and G0. So then T7 divide by gamma, and the phi 0 and G0 descend to this T7 on gamma because they're preserved by the gamma action. This is a compact G2 orbifold. So orbifolds are a kind of singular manifold where the singularities are modelled on R7 divided by some finite group, where the singularities come from the fixed points of elements of gamma. So if you've got some non-identity element of gamma which fixes some point in T7, then the image in T7 mod gamma will be a singular point. Okay, so we're hoping to fix these singularities and make it non-singular.
Gamma freely outside of
No, well, sorry, gamma act freely.
outside of the fixed point.
Yes, yeah. So we want gamma to have a faithful action. Otherwise, you might as well just take the quotient by the subgroup which fixes everything. Well, we're going to want at least. Well, we're going to need finite fundamental group. So we're going to need pi 1 of T7 on gamma to be finite, because otherwise we're going to end up with a 7 manifold with infinite fundamental group, which then cannot have holonomy spin 7. And we need singularities for this. Because if it was non-singular, then gamma would act freely, and then the fundamental group of that would be gamma semi-direct Z7, which would be infinite. Okay. So thirdly, not just any gamma will do. We have to arrange that the singular set of big gamma, of T7 mod gamma, is of a simple form which we know how to resolve. Okay, so actually back here, so then the simplest examples which work, as it were, would have gamma is Z2 cubed. Basically, if you had one Z2, you could reduce the holonomy to SU2. Two Z2s, you could reduce the holonomy down to SU3. If you want to get all the way to G2, you need at least something at least as big as Z2 cubed. Okay, so for example, in the simplest cases, the singular set of T7 mod gamma might be a disjoint union of copies of T3s, and near each T3 it should be locally modelled on T3 cross R4 over plus or minus 1. Okay, so that would be a 7 manifold, a 7 orbifold, which we actually know how to resolve, and then we can resolve modelled on T3 with a G flat cross y comma h, or indeed t squared h, where y is this, did I say it was called the Iguchi-Hansen space? Which is T star of what? T star CP1. Yeah, so The four manifold with Lomé SU2 are used in the Kummer construction. T star CP1, it's called the Iguchi-Hansen space. Okay. Right. So fourthly, we make a compact 7 manifold big X by resolving the singularities of the T7 mod gamma, where we're using these asymptotically locally Euclidean local models. So asymptotically locally Euclidean means asymptotic to a cone such as R4 mod a group or C3 mod a group. Okay, so then, well, pi 1 of x is finite as pi 1 of T7 mod gamma is finite, and usually the resolution process doesn't change the fundamental group. Okay, so fifthly, we make a family of G2 structures phi t gt on your compact 7 manifold X for t in some small interval 0 up to epsilon, where epsilon is small, by gluing local models with a partition of unity. And, well, we can arrange that. We can actually make the free form d phi t to be closed. We can't make the 4 form closed, but we can make the C0 norm of the 4 form small, order of t to the 4, in the same way that we got t to the 4 as our error in the Kummer construction for things. So 4 is basically comes from the codimension of the singularities. If we only had codimension 6 singularities, we get a 6 here. Riemann curvature of GT in the C0 norm is again order of t to minus 2. Injectivity radius GT is order of t. So it's the same things that we had before. So this is the a measure of the torsion of the G2 structure. So it's a balancing act. We have a G2 structure which has small torsion, but then the metric is kind of close to singular. So this is good, and these things are bad. But once again, the good wins. We prove that for small t greater than 0, you can deform phi t gt to a torsion-free G2 structure. Phi t twiddle gt twiddle, which is close to phi t. So one way of measuring that is that the C0 norm of phi twiddle t minus phi t is of size around about t to the half. And this is by analysis of some nonlinear elliptic PDE. So we use the kind of whole battery of techniques involving Holder spaces and Fred-hole maps and estimates, various kinds, and then we produce this by a kind of series solution. We basically make a series of corrections and then prove that the corrections get smaller and smaller, and therefore converges to a solution of the equation we want. Finally, as pi 1 of x is finite, one of the early propositions, proposition 5.2, I said, says that the Holonomy group of G twiddle T is G2, as we want. Okay, so, well, by choosing different groups gamma, and different resolutions, you can find many submanifolds. With Holonomy G2. So in my book, you can find a whole bunch of submanifolds. We get 252 different sets of Betti numbers. So potentially many more actual submanifolds, because the kind of variations on in the choice of construction here run into the millions, but I didn't actually distinguish, well, try to find whether you get the same submanifolds or not. Okay. All right, so there's also a second construction of compact G2 manifolds due to Kovalev and Corti, Haskins, Nordstrom, Pacini. That works by gluing together factors S1 cross a non-compact Calabi-Yau 3 manifold, which is asymptotic to a cylinder at infinity. So you take two of those and you kind of glue the cylindrical ends together with a kind of twist. And they give you actually quite a lot more sets of Betti numbers or G2 compact submanifolds. So we now know a reasonable number of examples. Now we only know how to construct compact submanifolds with Holonomy G2 by gluing together pieces which are either flat or flat times Calabi-Yau, where you get the Calabi-Yau metrics either explicitly, such as the Iguchi-Hansen metric, which is just written down in coordinates, or you can get the Calabi-Yau metrics by applying the Calabi conjecture to some compact or possibly non-compact but controlled complex manifolds. And there may be many G2 manifolds which you just can't access by these techniques because they don't break up in their limits into pieces, all of which are kind of flat cost Calabi-Yau. But we don't know that. I mean, basically this is, in the subject of G2, there's a lack of tools. There's lots of questions it's very difficult to answer because you can't imagine how you go about it. Anyway, sorry I've run over a bit.